Hello everyone, my name is Pratik Sangle and I am a final year BTech student from the Department of Cybersecurity at GHRCEM College of Engineering Pune. Along with my teammates Krutika Borase and Pranit Siddam, we have developed a major project titled Real-Time Edge Deployed LSTM for IoT Botnet and DDoS Anomaly Detection. This work has been carried out under the valuable guidance of Nishigandha Vyawahare ma'am, our HOD Dr. Deepika Azalkar ma'am, and our major project coordinator Professor Rupali Parthe ma'am. This project focuses on developing a complete end-to-end system that can detect malicious and abnormal activity generated by IoT devices in real time. We have designed a lightweight, edge-optimized deep learning model that can run directly on low-power hardware like a Raspberry Pi, without depending on cloud servers or heavy infrastructure. Throughout this presentation, I will be explaining the background of the problem, the motivation behind building this system, the design choices we made, the deep learning architecture we implemented, and finally a complete demonstration showing how the system works in real time. This includes everything from pre-processing the network data to training the model, deploying it on the edge device, and visualizing the results through our dashboard. The motivation behind this project arises from the rapid and widespread adoption of IoT devices in almost every sector today. Systems are now embedded into smart homes, healthcare equipment, industrial automation systems, surveillance networks, and smart city infrastructure. While this growth has improved convenience and efficiency, it has also created a massive increase in the number of potential attacks points for cybercriminals. Most IoT devices are designed with very limited preprocessing power and minimal built-in security controls. Many devices run outdated firmware, use default passwords, or lack proper authentication mechanisms. Bec- Because of these weaknesses, they often become the first targets for botnets, large-scale DDoS attacks, and automated exploitation tools. Traditional security solutions such as signature-based intrusion detection systems or cloud-based monitoring platforms are not suitable for handling modern IoT traffic. Signature-based systems can only detect known attacks and they fail when attackers change patterns or use zero-day techniques. Cloud-based detection introduces significant delay, consumes large amount of bandwidth, and exposes private user data to external servers. Moreover, IoT environments require immediate action because even a short delay in identifying an attack may allow malicious traffic to spread rapidly across networks or disrupt critical services. This growing risk and the limitations of existing systems motivated us to design a solution that works locally, instantly, and efficiently. Our aim was to build a detection mechanism that stays close to the IoT device, consumes minimal resources, preserves privacy, and reacts in real time to stop harmful traffic before it escalates. The central problem we address in this project is the lack of an effective real-time anomaly detection system that can run directly on edge. That is on small low-power IoT devices or gateway nodes. IoT devices generate extremely dynamic and high-volume network traffic, making it difficult to distinguish between normal and abnormal behavior using simple rules. At that same time, these devices do not have the computational capacity to run large machine learning models or deep packet inspection techniques that traditional security tools rely on. Cloud-based detection systems introduce delays, are vulnerable to connectivity issues, and require sending sensitive traffic of the local network, which creates privacy and compliance concerns. Heavy deep learning models, on the other hand, consume too much memory and fairly stated as follows: how can we de- detect anomalous botnet like or DDoS driven traffic in real time on low power edge device using a lightweight and accurate deep learning model that does not rely on cloud systems or heavy hardware? Before designing our system, we examined the existing solutions being used in the domain of IoT security and anomaly detection. Most traditional security mechanisms rely on signature based intrusion detection systems, which match incoming traffic against a predefined list of known attack signatures. While this approach works for already identified threats. It completely fails when the attacker modifies their behavior or uses new previously unseen patterns. Signature systems also require continuous updates and they cannot protect against zero-day attacks, making them unreliable for fast evolving IoT threats. Another category of solution involves cloud-based anomaly detection platforms where the traffic from IoT devices is continuously uploaded to cloud servers for analysis using powerful machine learning models. Although this allows the use of large and complex algorithms, it introduces critical challenges. Cloud-based systems depend heavily on stable internet connectivity, which may not be available in all IoT environments. They also introduce significant latency, meaning the detection happens after the malicious activities have already occurred. On top of this, sending raw network traffic to external servers violates privacy requirements and exposes sensitive information to third party cloud providers. In summary, existing solutions either rely on heavy patterns of known attacks, depend on remote cloud servers, or are too heavy for edge hardware. None of these approaches provide a reliable, low latency, privacy preserving, and easily deployable anomaly detection mechanism for real world IoT environment. This gap is what led us to design a new solution that focuses directly on edge based, lightweight, real time detection. As part of our literature survey, we examined research papers that explored intrusion detection mechanisms for IoT networks. A consistent theme in the research community is the growing interest in deep learning based anomaly detection. Because deep learning models can automatically extract complex patterns from raw data without requiring manually crafted rules. Many studies have shown that traditional rule-based systems fail to keep up with the modern attack variation, whereas neural networks can adapt and learn from traffic behavior itself. One significant insight from the literature was the effectiveness of an hybrid CNN-LSTM or CNN-BiLSTM models for analyzing network traffic. CNNs have proven to be excellent at capturing local patterns with a short time window of network features, while LSTMs have and BiLSTMs are particularly good at understanding the temporal relationship across multiple packets or flows. Another set of paper focused on the challenges of deploying these models in IoT environments. Researchers pointed out that IoT devices had limited memory and processing capacity, which prevent the use of large and complex models. Some studies propose lightweight architectures, quantization techniques, and edge-based inference to overcome the limitation. These works emphasized the importance of reducing the model size and optimizing execution to fit within the constraints of low power devices like Raspberry Pi. To address the limitations of existing systems, we propose a real edge deployed anomaly detection solution designed specifically for IoT environments. Our approach focuses on processing only 22 lightweight features extracted from the network traffic metadata, which makes the system fast, privacy preserving, and computationally efficient. These features capture essential behavior indicators such as flow duration, packet count, protocol type, source and destination ports, frame length, TTL values, and other statistical characteristics that allow the model to distinguish between normal and abnormal traffic patterns without requiring deep packet inspection. The core of our proposed system is hybrid CNN by LSTM deep learning architecture. In this design, the CNN layers focus on extracting local spatial features within short segments of traffic, while the BiLSTM layers learn temporal patterns and dependencies across time. This combination allows the model to understand how traffic evolves and how anomalies develop over sequences of network events. An additional attention or squeeze and excitation mechanism further improve accuracy by enabling the model to identify and emphasize the most important timestamps that influence the final prediction. Finally, the output is visualized through a Streamlit dashboard which displays live prediction, anomaly probabilities, logs, and trend charts. This complete pipeline from processing to training, optimization, deployment, and visualization forms a robust and practical solution that detects botnet and DDoS anomalies at the earliest possible moment directly at the edge. overall architecture of our system is designed to enable fast, efficient, and privacy-preserving anomaly detection at the edge of an IoT network. The architecture begins with the IoT devices such as smart cameras, sensors, routers, or any connected endpoint generating network traffic. Instead of sending this traffic to cloud server for heavy processing, we extract a minimal and carefully selected set of lightweight metadata features locally. These include basic flow statistics, packet counts, protocol identifiers, and timing features that allow us to capture the behavioral characteristics of traffic without accessing any sensitive payload information. Once the feature are extracted, they are sent to Mosquito MQTT broker, which acts as a central communication hub. MQTT is ideal for IoT environment because it is extremely lightweight, fast, and designed to handle continuous real-time message flow even on low-power network. The edge device, typically a Raspberry Pi or an IoT gateway, subscribe to MQTT topic and continuously receives incoming features into when a feature window arrives, it passes through our processing layer, which uses consistent artifacts generated during training, such as scalar.pkl for normalization, feature order.json to ensure correct feature alignment, and the clipbound.json to standardize output outlier handling. After preprocessing, the data is fed into our CNN-BiLSTM model, which has been clearly trained and calibrated. The CNN layer learns local traffic patterns when the BiLSTM layer understands the temporal evolution of traffic sequences. The model then produces an anomaly probability indicating whether the behavior is normal or malicious. After inference, the result is forwarded to the Streamlit dashboard, which displays the real alerts, probability graphs, and traffic trends. The modular architecture allows for smooth communication, consistent preprocessing, fast inference, and clear visualization, all running entirely on edge without cloud dependency. Conclusion: this project demonstrates that effective and reliable IoT anomaly detection can be achieved directly on edge devices without relying on cloud infrastructure or heavy computational resources. By designing a hybrid deep learning model that combines the spatial learning ability of CNNs with the temporal sequence understanding of BiLSTM, we were able to capture both static and dynamic characteristics of IoT network traffic. Our preprocessing pipeline ensured consistent and noise-free feature extraction while model calibration improved the stability and trustworthiness of the prediction. The complete system from feature engineering and training to optimization, deployment, and real-time visualization shows that lightweight models can perform exceptionally well when designed and tuned with edge constraints in mind. With quantization and honest optimization, the final model runs efficiently on low power hardware such as Raspberry Pi, providing millisecond level inference speeds that are essential for early detection of botnet and DDoS attack. Overall, this work bridges the gap between advanced and anomaly detection algorithms and real-world IoT deployment scenarios. It proves that edge-based deep learning solutions can be both accurate and efficient, making them a strong foundation for future IoT security architectures. Our project gets the groundwork for scalable, privacy-preserving, and real-time defense mechanisms that can evolve alongside modern IoT networks, ensuring safer and more resilient connected systems in years ahead. Thank you.